In this video, we are going to learn how to extend the method of Lagrange multipliers to multiple constraints. When looking at applications of Lagrange multipliers, this is a more realistic situation. So in order to maximize or minimize the function f of x, y, z, subject to two constraints now, g of x, y, z equaling 0 and h of x, y, z equaling 0. So we now have two constraint curves. So we have g and h, and the point has to be on both of those constraints. Then there are Lagrange multipliers, lambda and mu, for which the gradient of the function f at the point x0, y0, z0 is equal to lambda times the gradient of g at that point plus mu times the gradient of h at that point. So now we're looking for points where the gradient of the function is equal to a linear combination of the gradient of g and the gradient of h. And lambda and mu are now the Lagrange multipliers, the scalars that are going to make that sum equal to the gradient of the function f. Okay, so how do we extend the method that we've been doing? So we can still create a Lagrangian function. Now our Lagrangian function has x, y, z, lambda, and mu in it. So that's going to be f of x, y, z minus lambda times g of x, y, z minus mu times h of x, y, z. And we take now 5 partials to find the gradient with respect to x, y, z, lambda, and mu. That will create 5 equations that we need to solve. So let's look at an example where we do exactly that. So use Lagrange multipliers to find the maximum and minimum value of the function 2x plus y squared plus z squared on the constraints x squared plus y squared equal 1 and x minus z equals 0. Okay, so g of x, y, z, our first constraint curve is x squared plus y squared minus 1. Only in terms of x and y, that function, but the constraint could be in terms of all three. And then our constraint curve h of x, y, z is x minus z. Again, in terms of only two variables, it could be in terms of three. And in a way, because both these constraints are in terms of only two variables, that should make things a little bit easier. But we'll see as we get into the problem. Again, we're assuming that each of these curves is equal to 0. Okay, so now we have, and I just should clarify, these are constraint surfaces now, not curves, because we are working in 3 space. It's just habit to call them constraint curves when talking about Lagrange multipliers. So let's build our Lagrangian function. So f of x, y, z, lambda, mu. So that's 2x plus y squared plus z squared minus lambda times the constraint x squared plus y squared minus 1 minus mu times our other constraint x minus z. Okay, so now we need to find the gradient of this function that we created. So with respect to x, that's going to be 2 minus 2 lambda x and minus mu. Almost forgot the mu part. Right? We now have another term to differentiate. Then with respect to y, we have 2y minus 2 lambda y, and then no mu term. And then we have 2z, no lambda term, and then plus mu, negative 1 times negative mu. And then with respect to lambda, that would be the negation of x squared plus y squared minus 1. And with respect to mu, negation of x minus z. And just to recall, these last two components of the gradient vector are nothing more than the constraints. Right? Any point that we find has to now be on both of these constraints because there are 2 of them. So now we set each component equal to 0 because we're looking for where that gradient is the 0 vector. So 2 minus 2 lambda x minus mu equals 0. 2y minus 2 lambda y equals 0. 2z plus mu equals 0. And then our two constraints, I'll just stack them over here, x squared plus y squared equals 1, and x minus z equals 0. When we get to the point of finding the points on the constraint, we'll go to the next slide just to give ourselves some more space. So let's focus here on solving. So we have three equations that we need to solve, and picking the starting point can be the biggest challenge. Looking at the three, I'm going to focus on this middle equation because there is a 2y that can be factored out. So 2y and then 1 minus lambda equals 0. So then that means that either y equals 0 or lambda equals 1. So we have two cases that we have to explore further, the case where y equals 0 and the case where lambda equals 1. So if we take y equals 0 and we look in the other two equations, so there is no y term here. So as long as there's a lambda and a mu that make that 0, we'd be good. And the same thing here, as long as there's a z and a mu that would make that 0, we would also be good. So we've made it to the constraint curves. So we're going to take y equals 0, we're going to pause on that case, and we'll pick it up on the next slide. And now let's explore lambda equals 1. So if lambda equals 1, we can substitute it in here. So if lambda equals 1, this equation reduces to 2 minus 2x minus mu equals 0. And we can get mu in terms of z. So mu equals negative 2z. So then we can substitute that expression, negative 2z, for mu here. And the reason we'd want to do that is getting an expression in terms of x and z is great because we can relate the variables to one another. So then we can have 2z equaling to 2x minus 2, or z equaling to x minus 1. Okay, so if lambda equals 1, we were able to create a relation between x and z in the form of z equals x minus 1. So now we have two cases that we have to explore further in the constraint curves to see if there are critical points. We have y equals 0, and we have z equals x minus 1. Okay, so let's start with the y equals 0 case. So if y equals 0, then y has to be 0 in both constraint curves. Y is only in the first curve, so that means that x squared plus 0 squared equals 1. So x squared equals 1, x equals plus or minus 1. And we dive further now. Now we break into two more subcases. So if x is 1, well then we go into the other constraint. So then we'd have 1 minus z equals 0, 1 equals z. And then if x equals negative 1, we have negative 1 minus z equals 0, and negative 1 equals z. So through this subcase, we get two critical points. Y is 0 at both the points. When x is 1, z is 1, y is 0. So we have 1, 0, 1. And then negative 1, 0, negative 1. All right, so there are the first two potential points where the max or the min occur. Now we have to explore the other subcase, and that's if z equals x minus 1. So if z equals x minus 1, we're going into the constraint curve, so I'm going to pick the one that has x and z in it. So that means that x minus 1 equals 0. So x minus x plus 1 equals 0, 1 equals 0, which is not true, which means there are no points on the constraint curve x minus z equals 0 where z could be equal to x minus 1. So this relation that would have given us 0 in the gradient of the Lagrangian function doesn't yield any critical points. Okay, so that leaves us with just 2 points to test in the function. So we plug in both. So if we plug in 1, 0, 1, we're going to get 2 plus 0 plus 1, so that's 3. And negative 1, 0, negative 1, we're going to get negative 2 plus 0 plus 1. So that's going to be negative 1. Let's make sure, let's change the color back to black. So negative 1. So we have our max of 3 at the point 1, 0, 1, and the minimum of negative 1 at negative 1, 0, negative 1. So this is what it looks like when we have more than one constraint. And this case is pretty relatively easier. I don't want to say easy, I was going to, but it's not necessarily easy, but this can get quite complicated as the constraints incorporate 3 variables, as the constraints become more complex, and we would get to a point where we would probably look at using some sort of software to solve these. If we have 3, 4, 5 constraints, it would be a little bit difficult to do that by hand, right? So practice a few of these just so you can get used to using the mu Lagrange multiplier and how some of this works out.